Paris of the early 19th century was the place to be if you were a mathematician. Ampère was discovering the hidden link between electricity and magnetism, while Poisson was developing the complex maths to unite them. At the same time, Cauchy was laying down the rigorous rules for calculus that we still use today.
But it was here, in the illustrious halls of the École Polytechnique, that a legendary professor and his brilliant graduate fellow would propose two ideas that were so far ahead of their time it would take 200 years and the invention of the computer for the work of Pierre-Simon Laplace and Jean-Baptiste Joseph Fourier to unlock the modern digital age.
There was quite the professional rivalry between them. When Fourier submitted his masterpiece on heat in 1807, Laplace, who was one of the judges, refused to publish it. It took Fourier nearly 15 years of fighting, refining, and even being elected to the Secretary of the Academy himself before he could finally get his work published in its full form in 1822. To us, looking back through the lens of history, it seems strange that these two men should have been locked in such a fierce fight. Their ideas share so many commonalities that one must begin to wonder who stole what from whom. But the truth is far more fundamental, if a little mundane in the human drama department. They weren't stealing from each other, they were just coming at the same truth from two different angles. While Fourier was obsessed with the physical rhythm of heat, Laplace was seeking the underlying stability of the universe itself. Our reality obeys a set of rules. We call them the laws of physics. So if two people are studying different aspects of the same reality, it is logical that the rules they discover will eventually converge, regardless of the path they took to find them. Laplace and Fourier might have been in competition professionally, but there is no paradox in the singular truth they were both trying to describe. It was inevitable, therefore, that their ideas must eventually meet. Today, we don't choose between the Laplace and Fourier transforms, we use them together to drive the technology of our world, a world that Laplace and Fourier couldn't even imagine. So what is the Laplace transform? What is it for? How does it work? And what part do Fourier's theories play in Laplace's ideas? While the Fourier transform is superb for analysing signals once everything is up and running, it falls short when we consider things like the initial turn-on behaviour of an electrical circuit, or how a mechanical system settles after a sudden jolt. For such crucial transient behaviours, and to truly understand how a system converts an input into an output, we need a mathematical tool that can account for things like time-varying amplitudes and initial conditions. That tool is the Laplace transform. If you look up what the Laplace transform does in an encyclopedia, you'll probably find something along the lines of, the Laplace transform characterizes the impulse response of a linear time-invariant system. Okay, so what's a linear time-invariant system? And what's an impulse response? This is a linear time-invariant system. Yes, I know, it looks like a bowl. But this is a special type of bowl, called a Tibetan singing bowl. If I strike it with this stick, it rings like a bell. It's linear because if I strike it twice as hard, the sound it makes will be twice as loud. It's time invariant because if I strike it again now, in the same way as I struck it before, the sound it makes will be exactly the same. So, if this is our linear time-invariant system, what is the impulse it responds to? Well, it's the strike of the stick. Now, this stick is quite hard. When it strikes the bowl, it hits it with a short, sharp, sudden burst of force. If I were to plot how that force changes with time on a graph, it looks like a very narrow peak, almost a single vertical line. This is the impulse that sets the bowl ringing. The impulse response is the ringing sound the bowl makes when I hit it with the hard stick. What if I hit the bowl with the other end of the stick? The other end is covered in this felt material. When I use it to hit the bowl, the ring it makes is slightly different. It's duller, because the cushioning effect of the felt has changed the shape of the force it hits the bowl with. If I know the impulse response of the bowl and the force time graph of the stick used to hit it, the Laplace transform will help me predict what sort of ring the bowl will make. Now, trying to predict how a Tibetan singing bowl will ring is all very nice, but it's only one example of what Laplace can do. In the world of economics, for example, Laplace is used to build macroeconomic models to assess the risks of a shock to the system, like a sudden change in interest rates. Economists use Laplace to try and predict whether the economy will be able to absorb the shock and settle back to a stable equilibrium, or whether the change will trigger a period of violent oscillation, a boom-bust cycle, potentially throwing the whole economy into chaos and recession. But how does Laplace do this? How does it take the raw ingredients of the impulse and the system and use them to predict the future? To even begin to answer this question, we first need to ask another. How does the Laplace transform differ from the Fourier transform? Because while they are both deeply related, they serve two very different purposes. Why is Fourier so suited to analysing signals, while Laplace is the go-to tool for analysing systems? We'll find out in part 2.